Every few seconds, somewhere in the universe, a signal erupts with the energy of billions of suns and then vanishes in less than the blink of an eye. Scientists call them fast radio bursts, or FRBs. But here's the mystery. We don't know what or who is sending them. Are they the dying screams of collapsing stars? The heartbeat of something hidden at the edge of physics? Or could they be a message, pulsing through the cosmic static, waiting for us to decode? Tonight, we're diving into one of the strangest puzzles in modern science, the signals from deep space that should not exist. Since the dawn of civilization, humans have looked upward and felt the pull of the unknown. The stars whispered to our ancestors in silence, their steady glow, inspiring myths, calendars, and entire worldviews. But the universe has never been only about what we can see. Sometimes, it speaks in ways our eyes cannot perceive through vibrations of light and sound far beyond ordinary senses. It took the invention of radio astronomy for us to realize that the cosmos was humming, crackling, sending signals across unimaginable distances. And within that sea of signals, buried like a secret, humanity stumbled upon one of the greatest mysteries of modern science, the fast radio burst. To understand why this discovery was so profound, imagine the early days of listening to space. In the 1930s, a young engineer named Carl Jansky, working at Bell Labs, was tasked with finding the source of interference in transatlantic radio communications. What he found was astonishing, a steady hiss of radio noise coming not from Earth, but from the center of our galaxy. In that moment, a new field was born. For the first time, humans realized the heavens were not silent. They were alive with invisible signals. This was the start of radio astronomy, and it unlocked a hidden layer of the universe. Over the decades that followed, radio telescopes revealed pulsars rapidly spinning neutron stars, flashing with lighthouse-like precision, and quasars, unimaginably bright beacons powered by black holes. Each discovery reshaped our understanding of the cosmos. And then, in 2007, a graduate student named David Narkovic, analyzing old data from a telescope in Australia, found something stranger than all the rest. It was a signal so brief, it lasted less than a millisecond, yet in that instant, it released as much energy as the sun produces in days. This was the first recorded fast radio burst, a phenomenon no one had predicted. A cosmic heartbeat, brighter than billions of suns, hidden in the static. For years, some doubted it was real, perhaps an error in the data, perhaps interference from Earth. But as more and more of these bursts were found, the mystery deepened. They were not accidents. They were not artifacts. They were real. Fast radio bursts, or FRBs, are like cosmic whispers amplified to deafening shouts. Each one originates from billions of light years away, crossing oceans of space to reach our telescopes. And yet, by the time they arrive, they last less than the blink of an eye. Imagine standing in a thunderstorm, waiting for lightning to strike. The sky darkens, your senses sharpen, and then, for a fraction of a second, the world explodes in light and sound. That's what an FERB is, except the storm is a galaxy billions of light years away, and the flash carries more power than we can easily grasp. To put it in perspective, in a single millisecond, an FERB can unleash more energy than the total annual energy consumption of all of Earth's civilizations combined, multiplied trillions of times. It's an explosion so intense that if it occurred within our own galaxy, it might overwhelm every radio receiver on Earth. And yet, from billions of light years away, all we detect is a fleeting blip, a whisper hidden in the static of the cosmos. The fact that these bursts are so brief makes them devilishly difficult to catch. Telescopes must be scanning the right part of the sky at the right moment to capture one. For years, only a handful were known. Scientists would search old data and occasionally uncover a gem, but the bursts seemed random, unpredictable, like cosmic fireworks flaring without warning. And because they arrive from so far away, each one carries with it a record of the space it has traveled through. The signal is stretched, and distorted by clouds of gas, magnetic fields, and intergalactic plasma. Studying an FERB is like studying a message in a bottle, but one that has drifted across billions of light years, warped and weathered by the cosmic ocean. This is what makes FRBs such an irresistible mystery. They are at once powerful and fleeting, obvious and elusive. They tell us that somewhere in the universe, processes are at work that can generate energies beyond our comprehension, compress them into milliseconds, and hurl them across the cosmos. Yet we do not know exactly what those processes are. Are they the death throes of massive stars? The tantrums of magnetar's neutron stars with magnetic fields trillions of times stronger than Earth's? Collisions of exotic objects? Or, as some whisper half-jokingly, the beacons of an advanced civilization? The story of cosmic signals has always danced between the ordinary and the extraordinary. When pulsars were first discovered in the 1960s, their regular, clock-like signals seemed so artificial that the discoverers nicknamed them LGM, Little Green Men. Of course, pulsars turned out to be natural, but their discovery marked a turning point in how we listen to the cosmos. FRBs carry that same aura of strangeness. They sit at the edge of our understanding, refusing easy explanations, demanding new physics or new perspectives. And so, the mystery of cosmic signals is not just a story about astronomy. It is a story about us, about how we reach beyond what we know, straining to hear whispers across the void, about how, in the midst of static and noise, we catch glimpses of something greater. Fast radio bursts remind us that the universe is still full of surprises, that the cosmos is not a solved puzzle, but a living, breathing enigma. They are the faint voices of a universe far larger, stranger, and more powerful than we ever imagined, and we are just beginning to learn how to listen. The first chapter of this story leaves us with more questions than answers. What could create such immense energy in such a short time? Why are these bursts so rare, so scattered, and yet so bright? And most haunting of all, are we listening to natural phenomena or to something else? As the search continues, the mystery deepens. And for now, all we can do is keep listening to the sky, waiting for the next whisper from the dark. The story of fast radio bursts begins not with the flash of a telescope trained on the heavens, but with an accident of curiosity and patience. In 2007, at the Parkes Observatory in Australia, astronomers were sifting through years-old archival data when they stumbled upon something that didn't fit. A pulse, a flicker, a whisper that lasted just 5 milliseconds, the blink of an eye, stretched 1,000 times shorter. But in that infinitesimal slice of time, the signal carried with it an energy so staggering it dwarfed entire galaxies. This was not static, not noise, not interference. It was something real, and it came from billions of light years away. To appreciate how astonishing this was, we need to understand how astronomers listen to the universe. Radio telescopes do not capture images the way optical telescopes do. They capture patterns of energy, faint ripples of electromagnetic radiation washing across the Earth from space. These patterns are usually steady, predictable: the hiss of the Milky Way's disk, the rhythmic heartbeat of pulsars, the gentle glow of interstellar hydrogen. When something breaks that rhythm, astronomers notice. And in this case, what they noticed was an explosion compressed into a single, impossibly brief moment. The graduate student who first found it, David Narkovic, was not hunting for mysteries. He was combing through data from a pulsar survey, one of countless projects designed to catalog the universe's known radio beacons. Pulsars, after all, are reliable spinning neutron stars that send beams of energy sweeping through the cosmos like lighthouses. But buried in the noise of one dataset, there was something no pulsar could explain. A flash, a burst, 5 milliseconds of raw, unfiltered power. At first, no one knew what to make of it. Perhaps it was a glitch in the system, a computer hiccup masquerading as a cosmic event. Perhaps it was human interference, the ghost of a passing satellite or a burst of static from microwave ovens near the observatory. Skepticism ran high because the signal seemed too extreme to be real. In those 5 milliseconds, the burst released as much energy as the sun emits in nearly a month. It was as though the universe had coughed, and in that cough was the power of 10 million supervolcanoes erupting at once. But science thrives on repetition. One anomaly can be dismissed. 2, perhaps, are coincidence. But soon more bursts began to surface. As astronomers combed through more archival data, they found additional events, each one brief, each one blindingly powerful, each one arriving from far beyond our galaxy. They were not glitches. They were not interference. They were real, and they were happening often enough to suggest that the universe was littered with them. The comparison that quickly spread through astronomy circles was stark. It was as if the cosmos were firing invisible gunshots into the void. Each FERB was a bullet of energy, sharp, precise, and devastatingly quick. Imagine standing in an empty canyon, hearing the crack of a rifle shot echo from the cliffs, except in this case, the shot traveled across billions of light years before it reached your ears. The sheer improbability of detecting such a thing only deepened the mystery. The bursts were so brief that telescopes had to be staring at the right place at exactly the right time to catch them. It was as though the universe was testing us, dropping hints of a grander design, but offering only fragments. And yet, even fragments carry stories. Each FERB traveled through oceans of intergalactic plasma on its way to Earth, its signal stretched and scattered by every particle it encountered. To astronomers, that distortion was a gift. It meant the bursts could be used as probes of the cosmos itself, mapping the invisible matter that lies between galaxies. Suddenly, what had seemed like an inexplicable anomaly became a potential tool. FRBs could be not only a puzzle, but a window, a way to study the dark spaces of the universe that otherwise remain unseen. Still, the excitement was mixed with frustration. No one knew the origin of these bursts. Unlike pulsars, which repeat regularly, or quasars, which can be studied for years, FRBs seemed to appear and vanish at random. Some were brighter, some dimmer, some longer, some shorter. Each one unique, as if crafted by different hands. The lack of consistency made them maddening to study. They were real, yes, but what were they? Magnetars tearing themselves apart? Black holes colliding? Stars collapsing into exotic remnants? Or was it something even stranger, something we hadn't yet imagined? As the discoveries accumulated, the skepticism faded. Astronomers knew they were facing a new category of cosmic phenomenon. In 2013, the first paper describing multiple FRBs was published, cementing their reality and igniting a frenzy of research around the world. Suddenly, observatories everywhere were reanalyzing old data, building new instruments, and hunting for these fleeting bursts. The hunt became global, and with it, the sense of wonder grew. Humanity had stumbled upon a new cosmic language, one that spoke in bursts too fast for our eyes, but not for our machines. What makes the discovery of FRBs so haunting is not just their power, but their silence. They come without warning, without pattern, without explanation. A shot fired in the dark, then nothing. For scientists, this silence is both a challenge and an invitation. It forces us to stretch our imagination, to consider possibilities beyond the ordinary. It reminds us that the universe is not done surprising us. And so, what began as a faint blip in archival data has become one of the great mysteries of modern astronomy. A mystery that grows with every new detection, with every new burst cataloged. Each signal is a reminder that the universe is vast, dynamic, and full of phenomena we have yet to comprehend. Each one carries within it the possibility of discovery, the potential to reveal something profound about how reality works. The discovery of FRBs was not just the finding of a new kind of signal. It was a turning point, a reminder that even in an age of advanced technology, the universe still holds secrets capable of humbling us. Each burst is like a message in a bottle, drifting across billions of years and landing, by chance, in our instruments. And though we may not yet know the author of those messages, or even the language they are written in, one thing is clear: the universe has more to say. We just have to keep listening. When we talk about fast radio bursts, the first thing that comes to mind is their brevity flashes of energy that come and go in less than the blink of an eye. But what truly elevates them into the realm of cosmic legend is not their shortness. It is their power. Imagine a single, solitary pulse that lasts only 1,000th of a second, yet in that instant releases more raw energy than our sun produces in an entire year. The sun, our life-giving star, has burned steadily for 6 billion years, fusing hydrogen into helium, radiating heat and light, sustaining life on Earth. It takes 12 months for the sun to generate the same output that one FERB produces in less than a heartbeat. And here's the kicker: these bursts don't come from nearby. They come from galaxies, billions of light years away, their signals traveling across cosmic gulfs of time and space just to reach us. For them to be visible at all from such unimaginable distances, they must be so powerful at the source that our usual metaphors crumble. Try, for a moment, to put that power into human terms. Picture every nuclear weapon ever built on Earth detonated at once. Multiply that by every nuclear weapon that could possibly be built in every city, on every continent. Multiply that by millions. You are still nowhere close. Or imagine harnessing the energy output of every single power plant on Earth, every wind turbine, every solar farm, every generator running non-stop for billions of years, and compressing that output into a single millisecond flash. That is closer, but still insufficient. These bursts are so mighty that when they first appeared in the data, many scientists were reluctant to believe they were real. How could nature produce such concentrated violence in such a tiny moment? Even the scale of their journey adds to their mystery. By the time an FERB reaches our radio telescopes, its energy has been stretched, scattered, and diluted across billions of light years. Space itself, expanding as the signal travels, has redshifted the burst, weakening it. Intergalactic clouds of gas and plasma have smeared it, like fog diffusing the beam of a flashlight. And yet, after all this, what remains is still strong enough to register on Earth as a clear, sharp signal. If this is what we detect at the end of its journey, then the original explosion at its source must have been beyond staggering. We struggle with metaphors because human imagination was never built to grasp such scales. The forces behind FRBs operate in extremes of density, extremes of magnetism, extremes of gravity. Consider magnetars, one of the leading suspects in the FERB mystery. These are neutron stars, the collapsed cores of massive stars so dense that a single teaspoon of their material would outweigh Mount Everest. Now, add magnetic fields 1,000 trillion times stronger than Earth's. A starquake on such an object, a sudden snap in its crust, could unleash energies that ripple through the universe as radio bursts. But can even magnetars explain the most luminous FRBs? Some researchers think so. Others argue the brightest events still defy explanation. There is also the question of time compression. Most cosmic events are stretched out. A supernova unfolds over days or weeks. A gamma-ray burst might last seconds to minutes. FRBs, by contrast, funnel their fury into milliseconds. It is as though the universe is not just shouting, but screaming at the highest possible pitch, concentrating unimaginable energy into the smallest possible container. This compression is part of what makes them so incomprehensible. Nature rarely operates in such tightly wound bursts. To do so requires mechanisms that we barely understand, involving physics at the limits of what we can test. To astronomers, the raw power of FRBs is both a challenge and a gift. A challenge, because we must stretch our theories to account for energies that make even supernovae look tame by comparison. A gift, because such power can be used as a tool. These bursts, traveling across the cosmos, can illuminate the invisible. They can probe the space between galaxies, revealing the hidden distribution of matter that ordinary light cannot show. In this sense, FRBs are like cosmic flashbulbs, momentarily lighting up the dark corridors of the universe. But to understand the sheer magnitude of their power, we can return to something more familiar, our Sun. Imagine its steady fusion, its comforting warmth, its reliable rhythm. Now imagine condensing an entire year of that output into 1,000th of a second. That is what an FRB does. And then imagine that this condensed blast is hurled not across a solar system, not across a galaxy, but across billions of light years, and still it arrives strong enough to be detected. The mind stumbles at this scale. Words falter. The numbers we use begin to lose meaning. We enter a realm where human comprehension strains, where we are forced to admit that the universe is capable of phenomena we have not yet imagined. And so, when we talk about the power of FRBs, we are not just talking about numbers, about watts and joules and light years. We are talking about a mystery of nature at its most extreme. Whatever causes these bursts, it operates in a domain where our physics feels fragile, where our metaphors collapse, where awe is the only adequate response. The brevity of the bursts makes them elusive, but their power makes them unforgettable. They are the gunshots of the cosmos, the thunderclaps of distant galaxies, the screams of forces we do not yet understand. Each new detection is a reminder that we live in a universe still full of surprises, still capable of outpacing our imagination. FRBs are not just events. They are challenges, invitations to expand the boundaries of human thought, to stretch science until it matches the grandeur of reality. And until we understand them, they remain among the most extraordinary mysteries we have ever encountered, a fleeting whisper that carries the power of suns. When fast radio bursts were first discovered, one of the things that made them so perplexing was their apparent randomness. They arrived without warning, flared for a fraction of a second, and were gone. For years, astronomers assumed each FERB was a one-off event, a catastrophic cosmic detonation that happened once and never again, perhaps the final scream of a collapsing star or the death cry of an object being devoured by a black hole. A single shot fired across the void, never to be repeated. But then, something unexpected happened. In 2012, astronomers studying the sky with the Arecibo radio telescope in Puerto Rico detected a burst that refused to behave like the rest. It came again and again. The same patch of sky kept flaring, sending millisecond pulses weeks or months apart. Suddenly, the notion of FRBs being one-time only cataclysms was shattered. Some of these bursts were repeating. That simple fact transformed the mystery from strange to extraordinary. Repeating FRBs suggested that at least some of the sources were not one-and-done explosions. Instead, they were engines, cosmic machines that could fire more than once. That changed everything. If an FERB could repeat, then it was not necessarily the death of a star, but perhaps the ongoing tantrum of something still alive. The suspects shifted. Maybe magnetars flexing their impossibly strong magnetic fields. Maybe young neutron stars spinning and crackling with energy. Maybe exotic interactions we had not yet imagined. Whatever they were, their persistence opened new doors for study. The repeating bursts also provided scientists with something they had desperately lacked: predictability. A one-time FERB is almost impossible to study. By the time you notice it, it's already gone. You can't turn another telescope toward it, can't capture it across different wavelengths, can't prepare. But a repeating FRB offers a second chance and a third and a fourth. It allows astronomers to camp their instruments on a single point in the sky, waiting patiently for the next flash. With each repetition, we gather more clues. And then came the strangest discovery of all. In 2020, astronomers analyzing data from the CHIME radio telescope in Canada found a repeating FERB with a clear, uncanny rhythm. Every 16 days, like clockwork, the burst reappeared. It was as if the universe had set a metronome, tapping out a beat across billions of light years. For 12 days, the source was quiet. Then, for 4 days, it would fire bursts, one after another. Then silence again, repeating in a cycle. A cosmic rhythm, precise and deliberate, echoing across space. This discovery raised the stakes. Random bursts could be dismissed as the chaotic tantrums of extreme astrophysical objects. But a repeating cycle that hinted at structure, at order, at a physical mechanism we might eventually decode. Was the source orbiting something? Perhaps a companion star or a black hole? Its bursts modulated by the geometry of its orbit? Was it spinning, wobbling like a cosmic top, with its beams sweeping past Earth on a schedule? Or in the most speculative corners of discussion, was it artificial, the signature of some intelligence, pulsing deliberately? Astronomers are cautious. Most believe the cycles are natural, driven by orbital mechanics or magnetic precession. But the fact that nature can generate such regularity at such enormous energy scales is a wonder in itself. It reminds us that the cosmos is not random chaos, but a place where rhythm and pattern emerge from forces beyond our comprehension. And yet, not all repeaters are so orderly. Some fire off with irregular intervals, erratic and unpredictable. They might burst several times in an hour, then go quiet for weeks. This irregularity only deepens the mystery. Why do some FRBs repeat like clockwork while others are wildly inconsistent? Are there different classes of sources, different mechanisms at work? Or are we simply seeing fragments of a larger pattern we don't yet understand? The repeating bursts are like voices in a crowd. Some speak once and vanish into the noise. Others shout again and again, demanding attention. A few even chant in rhythm, daring us to decode their message. Each kind tells us something different about the underlying engines that power them. The one-time bursts may indeed be catastrophic collisions, collapses, cosmic accidents never to be repeated. But the repeaters hint at processes that persist, that endure, that might allow us to peer more deeply into the physics of their creation. What is certain is that repetition has transformed the FERB puzzle. Without repeaters, we would still be guessing in the dark, trying to piece together the nature of an event too fleeting to study. With them, we now have laboratories in the sky, cosmic machines that give us multiple opportunities to listen. Each repeating burst is like a drumbeat, a rhythm echoing across the void, reminding us that the universe is alive with phenomena we have only begun to glimpse. And so, the stakes grow higher. The more we study these repeating signals, the more we realize they are not accidents. They are telling us something, inscribing patterns into the cosmos that we are only now beginning to hear. Nature has given us riddles disguised as rhythms, whispers disguised as shouts. The question is not whether they mean something, the question is whether we are clever enough, patient enough to understand. When scientists first confronted the mystery of fast radio bursts, they did what science always does in the face of the unknown. They began with what is known. Instead of leaping to extraordinary explanations, they searched for natural ones, rooted in the extreme but familiar astrophysical phenomena we already understand, or at least think we understand. The universe is filled with violent, exotic objects capable of releasing staggering amounts of energy. Surely the reasoning went. FRBs must be the echoes of those cosmic catastrophes. And so began the search for natural explanations. The first and most compelling suspects were magnetars. These are neutron stars, the collapsed cores of massive stars that died in supernova explosions. Imagine cramming the mass of the sun into a sphere only about 20 kilometers wide. The result is a star so dense that a teaspoon of its matter would weigh more than Mount Everest. Now, at a magnetic field 1,000 trillion times stronger than Earth's. This is a magnetar, one of the most extreme objects known to science. Magnetars are violent by nature. They quake, they flare. Their magnetic fields twist and snap like cosmic rubber bands, releasing bursts of radiation across the spectrum. A single starquake on the surface of a magnetar could, in theory, unleash an FERB, a crack in the crust sending shockwaves through space. Magnetars explain many features of FRBs. Their immense magnetic fields can generate the right conditions for intense radio emission. They can repeat. Since a magnetar doesn't explode once and vanish, it can rumble and flare many times over its lifetime. In 2020, astronomers even caught a magnetar in our own galaxy, producing a burst of radio waves remarkably similar to an FERB, though far less powerful. This was the first direct link between FRBs and magnetars, and it electrified the scientific community. At last, there was evidence that at least some FRBs were natural tantrums of these stellar beasts. But magnetars alone cannot solve the puzzle. Some FRBs are far too luminous to be explained by known magnetar mechanisms, at least with our current models. Others repeat with uncanny regularity, a precision that seems difficult to reconcile with the chaotic nature of starquakes. Magnetars may be part of the story, perhaps even a large part, but they are not the whole story. Another possibility lies in collisions, the violent mergers of neutron stars, or black holes. When these titans collide, they release bursts of energy that ripple across the universe as gravitational waves. Could they also emit FRBs? Some theories suggest that as the magnetic fields of colliding neutron stars intertwine, they could produce a final, catastrophic pulse of radio energy before merging into a black hole. Such an event would explain one-time FRBs, those that flare once and never again. But it cannot account for repeaters, because a merger is a terminal event. Once two neutron stars collide, there is no second chance. Then there are supernovae, the explosive deaths of massive stars. In these cataclysms, a star expels its outer layers in a brilliant display, leaving behind a compact remnant. Some models propose that in the moments before or after such an explosion, conditions might briefly exist to produce an FERB. Again, this could explain one-off bursts, but not repeaters. Other exotic astrophysical ideas have been put forward. Some suggest FRBs might be linked to the evaporation of primordial black holes, tiny relics from the Big Bang disappearing in a final flash of energy. Others point to cosmic strings, hypothetical defects in space-time itself, predicted by certain theories of the early universe. If two cosmic strings were to snap or collide, they might send a burst of radio waves rippling outward. These ideas are tantalizing but speculative, lacking the direct evidence that magnetars enjoy. The difficulty with every natural explanation is diversity. FRBs are not uniform. Some are faint, some blindingly bright. Some last less than a millisecond, others linger for several milliseconds more. Some repeat erratically, others with uncanny rhythm. A single explanation struggles to fit all these behaviors. Magnetars explain the repeaters, but not the brightest bursts. Collisions explain the one-timers, but not the cyclical patterns. Supernovae explain catastrophic events, but not the ongoing engines. Each theory explains part of the puzzle, but none capture the whole. This has led some astronomers to suspect that FRBs are not a single phenomenon, but a family of phenomena. Perhaps magnetars produce many of them, but collisions produce others. Perhaps nature has multiple ways to create a cosmic radio flash, and we are seeing them all superimposed. Just as gamma-ray bursts turned out to have both short and long classes with different origins, FRBs may also have multiple categories hidden within their diversity. The puzzle deepens with every discovery. In the early years, only a handful of FRBs were known, and scientists could fit them into simple models. Now, with hundreds cataloged and more discovered every week, the data shows complexity that resists easy answers. Patterns emerge, only to be broken by exceptions. One repeating FERB follows a neat cycle, another bursts unpredictably. One is faint and close, another so powerful it defies known physics. The deeper we look, the stranger they become. And yet, this is the essence of scientific discovery. We begin with natural explanations, because the universe has always surprised us with its ability to generate phenomena stranger than fiction. Pulsars once seemed artificial, quasars once defied understanding, gamma-ray bursts once baffled astronomers. In every case, natural explanations eventually prevailed, revealing mechanisms more exotic and fascinating than anyone had imagined. FRBs may follow the same path. The answers may lie not in alien civilizations or cosmic conspiracies, but in the restless violence of the universe itself, stars collapsing, magnetars quaking, black holes colliding. Still, until the pieces fit together, the mystery remains. Each new FERB is like a clue in a puzzle whose picture we cannot yet see. Natural explanations illuminate part of the board, but shadows remain. And in those shadows lies the possibility that we are on the verge of uncovering something truly new, something that will change our understanding of the cosmos yet again. Whenever science encounters a mystery too vast, too strange, or too unexpected to easily explain, the imagination leaps to the most dramatic possibility of all: aliens. It's almost a reflex. When pulsars were first discovered in the 1960s, their regular pulses were so precise, so clock-like, that astronomers half-jokingly called them LGM, little green men. Of course, pulsars turned out to be neutron stars, the rapidly spinning remnants of supernova explosions. But the instinct is telling. Whenever we hear a signal we cannot explain, the question rises, whispered at first and then shouted in headlines. What if it's not natural? Fast radio bursts fit this mold perfectly. They are sudden, bright, and brief. They carry inconceivable amounts of energy across billions of light years. And some of them even repeat, occasionally with uncanny rhythm. If you wanted to imagine what a distant beacon might look like, a message fired across the void by some intelligence beyond our own FRBs could fit the bill. They arrive like cosmic Morse code, dots and dashes written in millisecond bursts, whispering from galaxies so far away we will never touch them. The first serious speculation about aliens and FRBs came almost as soon as the bursts were confirmed. After all, if magnetars, black holes, and other natural explanations failed to cover every case, could it be that a few signals were engineered? Some researchers suggested FRBs could be beacons, deliberate attempts to signal across the galaxy. Think of a lighthouse on a rocky coast, its beams sweeping across the dark ocean. A civilization advanced enough could build a radio lighthouse, firing energy bursts into the cosmos, confident that other intelligent beings with radio telescopes would eventually notice. We might just be standing on the shore, catching the glow of a beam meant for someone else, or perhaps meant for us. Others have pushed the speculation further. What if FRBs are not messages, but technology at work? Harvard astronomer Avi Loeb and his colleague Manas V. Lingam suggested in 2017 that FRBs might be the byproduct of an alien propulsion system, vast radio beams used to push spacecraft across interstellar space. Imagine a sail, but not of cloth and not filled with wind. Imagine instead a gigantic sheet stretched in the void, propelled forward by beams of concentrated radio energy. The civilization behind such a system would need unimaginable power, perhaps harvesting the energy of an entire star, but the payoff would be equally unimaginable. Ships moving at fractions of the speed of light, crossing the gulfs between stars in timescales, not of millennia, but centuries or even decades. If such a system were in operation somewhere in the cosmos, its beams might leak energy into space. And we, eavesdropping with our telescopes, might interpret those leaks as fast radio bursts. Is this far-fetched? Absolutely. But is it impossible? Not entirely. The universe is old. Our civilization has existed for a blink of cosmic time. If life can arise on Earth, it can arise elsewhere. And if it can arise elsewhere, it can evolve, expand, and perhaps master technologies we can only dream about. For us, building a galaxy-spanning beacon or a star-powered propulsion system seems absurd. For a civilization millions of years older, it might be trivial. And yet, scientists are careful here. To invoke aliens too quickly is to abandon the harder, slower work of finding natural explanations. The principle known as Occam's razor guides much of science. The simplest explanation that fits the evidence is usually the correct one. FRBs may be exotic, but they still fit within the realm of extreme astrophysical phenomena like magnetars. To leap to aliens without exhausting natural explanations risks falling into fantasy. After all, pulsars once seemed like signals too. Quasars once seemed impossible to explain. Both turned out to be natural, though no less wondrous for it. FRBs may well follow the same path, but dismissing aliens entirely may be premature too. Science thrives on open minds, and FRBs keep that openness alive. When we ask, what if? We sharpen our imaginations, even if the answer turns out to be mundane. And the idea that somewhere, someone might be sending signals across the stars has a power beyond evidence. It forces us to confront our place in the cosmos. It humbles us, excites us, terrifies us. It asks us to consider the possibility that we are not alone. There's another angle to this speculation that is harder to shake. FRBs are extraordinary in both power and precision. They come from vast distances, yet arrive in bursts that we can detect clearly on Earth. They cross billions of light years and still retain their shape, their identity. That alone makes them feel engineered, as if someone had designed them to survive the journey. Even their repetition in some cases feels like intentionality, like a cosmic hand tapping out a rhythm to ensure we do not miss it. It may be natural, yes, but it feels deliberate. Imagine for a moment that one of these repeating FRBs is a message. Imagine that buried in the milliseconds of data is a pattern, a code. What would it say? Would it be a greeting, a warning, a demonstration of power, or something beyond our ability to decode, a message written in a language of mathematics or physics we do not yet understand? The thought alone is enough to fuel both wonder and unease. And what about the idea of propulsion? Picture a civilization building radio beams, not as communication tools, but as engines. Ships the size of cities sailing on invisible winds, crossing the void. Each time they fire their beams, the energy spills into space, detectable across the cosmos as a burst. We, sitting on our tiny planet, might be mistaking their traffic for natural phenomena. For them, it might be routine, just the noise of commerce, the hum of an interstellar highway. For us, it is a cosmic riddle, a puzzle that has consumed some of the brightest minds on Earth. The truth is, we do not know. The exotic theories are compelling precisely because they embrace our ignorance. They admit that the universe is stranger than we expect, and that intelligence may be one of its phenomena. They force us to keep our minds open, to balance skepticism with wonder. For every scientist who says, "It's surely magnetars," there is another who quietly admits, "But what if it's not?" In the end, FRBs sit at the boundary between science and speculation, between what we can measure and what we can imagine. The alien hypothesis may not be the answer. In fact, it probably isn't, but it serves a vital role. It reminds us that the universe is not just a machine to be cataloged, but a mystery to be engaged with. It reminds us that the strangest explanations sometimes turn out to be true, and that we must never close the door on possibility. So when we listen to those bursts, we may be hearing magnetars cracking, stars colliding, or plasma roaring. Or just maybe we are overhearing the hum of another civilization's technology, the whispers of minds far older and greater than our own. The signals are ambiguous. The interpretations are many. And the truth, whatever it is, will force us to rethink our place in the cosmos. What is certain is that FRBs, whether natural or artificial, stretch the limits of our imagination. They make us wonder not only about what lies beyond, but about who. And that, perhaps, is their greatest power, not in proving the existence of aliens, but in reminding us to keep asking the question. The hunt for the origins of fast radio bursts has become one of the most ambitious detective stories in modern astronomy. To understand just how challenging this quest is, imagine standing in a dark forest at night, blindfolded, while someone far away fires a gun that you can only hear for the briefest fraction of a second. You hear the shot, but by the time you remove the blindfold and look around, the echo is already gone. Now imagine trying to trace that sound back, not to a tree or a ridge, but to a point on the other side of the planet. That is the scale of difficulty astronomers face when they try to track FRBs back to their homes in the universe. A fast radio burst lasts mere milliseconds. A blink is 100 times longer. By the time the signal registers on a radio telescope, it's already over. Unlike a supernova, which can glow for weeks, or a quasar, which can shine steadily for billions of years, an FERB is ephemeral. Catching one is luck. Pinpointing its exact source is a miracle of timing, technology, and persistence. In the early years, when only a handful of FRBs were known, scientists were often left with frustration. They had proof that bursts existed, but no clear idea of where they came from. Each detection was like finding a message in a bottle with no return address. The sky is vast, and radio telescopes usually scan broad swaths of it, meaning the location of a burst might be uncertain by millions of light years. Without precision, astronomers could not link FRBs to specific galaxies, stars, or environments. They knew the universe was shouting, but they couldn't find the mouth. That began to change with the rise of new technology. Instruments like CHIME in Canada, ASKAP in Australia, and FAST in China were designed not only to detect FRBs, but to localize them to triangulate their positions with far greater accuracy than ever before. Suddenly, the mystery gained a new dimension. Astronomers could begin to answer the crucial question, where in the universe do FRBs live? The first major breakthrough came in 2017, when astronomers succeeded in tracing a repeating FERB known as FERB 121102 back to its home galaxy. The feat required coordination across multiple observatories, each one zeroing in on the same patch of sky until the location was nailed down. The result was astonishing. FRB 121102 came from a tiny dwarf galaxy more than 3 billion light-years away. Not a massive spiral like the Milky Way. Not a giant elliptical. A small, faint galaxy bursting with unusual star-forming activity. This was the first true return address on an FERB, and it reshaped the search. Why a dwarf galaxy? Why a region of furious starbirth? Some astronomers proposed that magnetars, the exotic neutron stars thought to power, many FRBs are more likely to form in such chaotic environments. Others wondered if there was something unique about the conditions in small galaxies, some hidden ingredient that nurtures the engines of FRBs. Still others pointed out that the link raised more questions than it answered. If FRBs only come from star-forming dwarfs, why had we detected so many from across the sky? Surely they had other homes as well. And indeed, further discoveries confirmed that FRBs are not limited to one type of environment. Some have been traced to spiral galaxies, others to elliptical ones, some near galactic centers, others at the outskirts. The picture is messy. Each new FRB adds data, but also adds complexity. There is no single environment that explains them all. Like detectives chasing multiple suspects, astronomers have realized they may not be looking for one culprit, but many. Pinpointing FRBs is not just about astronomy. It is about technology pushing the limits of precision. A burst lasting milliseconds must be captured in real time and cross-checked across multiple detectors. This requires arrays of telescopes spread across continents, linked by supercomputers that sift through oceans of data. At CHIME, for example, The telescope scans the entire northern sky every day, recording terabytes of information. Within that torrent of noise, algorithms must flag the fleeting fingerprints of FRBs and triangulate their origins. It is like listening to billions of conversations in a crowded stadium and isolating a single whispered phrase and then determining which seat it came from. Each success feels monumental. Every time astronomers pin down the home of an FERB, it's as though a light comes on in a dark room, illuminating a corner of the puzzle. But with illumination comes paradox. The diversity of host galaxies suggests that FRBs are not a single phenomenon. The engines that power them may differ. Some may indeed be magnetars, born from recent supernovae in star-forming galaxies. Others might involve interactions with black holes in older galaxies. Some may be catastrophic, others persistent. The more we trace, the more the picture fragments. And yet, even this fragmentation is progress. By learning where FRBs live, we narrow the field of possibilities. We learn which theories survive and which must be discarded. We gain not only clues about the bursts themselves, but tools to study the universe at large. Every FERB is like a lighthouse shining through the fog of intergalactic space. By measuring how the signal is smeared and scattered on its way to us, astronomers can map the otherwise invisible matter that lies between galaxies. In this way, the hunt for the origins of FRBs is not just about solving one mystery, but about opening a new window onto the cosmos. Still, the work is far from done. Hundreds of FRBs have now been cataloged, and more are detected every week. Yet only a fraction have been localized with precision. For every success, there are dozens more bursts that vanish without a trace, their homes still unknown. It is a race against chance, with telescopes waiting in silence for the universe to whisper again. The stakes are high because each discovery has the potential to rewrite the story. A repeating FERB tied to a dwarf galaxy was the first breakthrough. But what if one is traced to the edge of a black hole's accretion disk? Or to the heart of a globular cluster? Or to some environment we have not even considered? Each possibility carries implications for what FRBs are and what they are not. And so, the hunt continues relentless, meticulous, filled with frustration, but also with awe. Astronomers know they are chasing lightning, but lightning with meaning. Each millisecond burst is a postcard from across the universe, and every time we pin down its sender, we inch closer to understanding. Yet, the deeper truth may be that FRBs are not a single story, but many, a chorus of cosmic voices speaking in different tones. Each localization, each galaxy, each burst is another syllable in a language we are only beginning to learn. What is certain is that the search itself has changed us. In trying to find the origins of these bursts, we have built new telescopes, developed new algorithms, and expanded our ability to listen to the universe. Even if the full answer remains elusive, the act of hunting has widened our vision, sharpened our tools, and deepened our sense of wonder. The mystery of FRBs is still unsolved, but with every discovery, the fog lifts just a little more. And perhaps that is the point, that the universe reveals itself not all at once, but in bursts. The story of fast radio bursts is not just a tale of cosmic mystery, it is also a triumph of human ingenuity. For centuries, we've stared at the sky with naked eyes, then with glass lenses, then with arrays of mirrors and detectors. Each leap in technology has opened new frontiers. We discovered the planets with telescopes of glass, galaxies with mirrors of silver, the microwave afterglow of the Big Bang with antennas meant for satellites. But when it comes to FRBs' fleeting radio whispers lasting milliseconds, the challenge is unlike any we've faced before. To hear them, we've had to build machines that push the limits of engineering, computation, and patience. At the heart of this revolution is CHIME, the Canadian Hydrogen Intensity Mapping Experiment. Nestled in British Columbia, CHIME is not a traditional dish-shaped telescope. Instead, It looks like four long, curved half-pipes of metal, each the length of a football field. Unlike giant dishes that swivel to follow the sky, CHIME doesn't move at all. Instead, it simply stares upward, letting the rotation of Earth sweep the sky overhead. As the heavens drift by, CHIME's thousands of radio receivers collect torrents of data petabytes of it every day, sifting through the static of the universe for the faint fingerprints of FRBs. What makes CHIME revolutionary is its ability to scan the entire northern sky every single day. Before CHIME, FRBs seemed rare, like exotic fireworks glimpsed once in a while. But CHIME changed that perception overnight. It revealed that FRBs are not rare at all. In fact, they are happening constantly, all around us. Bursts flash across the sky thousands of times a day, perhaps even every second somewhere in the universe. We simply lack the tools to hear them. With CHIME, the sky became alive with signals, a chorus of cosmic static punctuated by sudden shouts. Then there is FAST, the 500-meter aperture spherical telescope in China. Nestled in a natural bowl between hills in Guizhou province, FAST is the largest single-dish radio telescope on Earth. Picture a radio ear half a kilometer wide, straining to catch the faintest whispers from across the cosmos. With its immense size and sensitivity, FAST has joined the hunt for FRBs with breathtaking success. It can capture bursts too faint for other telescopes, revealing layers of detailed tiny substructures within the millisecond flashes, fine patterns that might hold the keys to their origins. Where CHAME is broad and sweeping, FAST is precise and piercing, complementing each other like wide-angle lens and microscope. Together, CHIME and FAST are rewriting the story of FRBs. Before them, astronomers could count detections on their fingers. Now, the numbers soar into the hundreds and thousands. Instead of isolated curiosities, FRBs are becoming a catalog population, their diversity laid bare. We now know that some repeat often, some rarely. Some are faint, some blindingly bright. Some whisper in regular rhythm, others stutter unpredictably. The variety is staggering, and only such powerful instruments could reveal it. But it's not just the size of these telescopes that matters. It's also the computing power behind them. An FERB is a needle in a haystack of data. CHIME alone records terabytes every second, oceans of cosmic noise through which only a handful of FRBs hide. To find them requires sophisticated algorithms, machine learning systems that can recognize the telltale signatures in real time. Without this digital intelligence, the bursts would vanish unnoticed, drowned in the roar of the cosmos. In this sense, the true telescope is not just metal and wire, but silicon and software. The revolution doesn't stop with CHIME and FAST. Other instruments, like ASKAP in Australia and Meerkat in South Africa, add to the hunt with their own specialties. ASKAP's network of dishes, spread across kilometers, excels at pinpointing FERB locations with extraordinary accuracy, tying bursts to host galaxies. Meerkat, with its sensitivity and resolution, helps unravel the fine structure of bursts. Together, these telescopes form a global network, a kind of planetary ear tuned to the cosmic radio. The impact of this technological revolution is profound. Before, FRBs were singular mysteries. Now, they are a population study. Instead of marveling at a single signal, astronomers can compare hundreds, searching for patterns. They can ask statistical questions. How often do bursts repeat? Do they cluster in certain types of galaxies? Do their energies follow a distribution, or are there distinct categories? Each answer adds a piece to the puzzle. And with every discovery, the universe seems stranger. CHIME has revealed bursts so faint and frequent that it's clear the cosmos is littered with them, far more than we imagined. FAST has uncovered repeating FRBs with intricate subbursts, as if the signal is carved into syllables, each one layered with meaning. ASKAP has traced bursts to galaxies billions of light years away, their signals stretched and distorted by the matter they passed through. Each tool uncovers a different angle, and together they paint a picture of a universe far more active and dynamic than we once believed. Perhaps the most profound realization is this: the universe has always been shouting. For billions of years, FRBs have been flashing across space unnoticed. It is only now, with our new instruments, that we've begun to listen. The silence we once assumed was not silence at all, but our own deafness. The cosmos is alive with sound, bright, bewildering, and we are finally tuning in. This has philosophical weight as well. Every leap in our tools has expanded our sense of reality. Galileo's telescope showed moons around Jupiter, shattering the notion that Earth was the center of all things. The Hubble Space Telescope revealed galaxies stretching to the edge of time. Now, CHIME and FAST reveal that even the dark, radio-silent universe is alive with bursts we never knew existed. Each tool does not just expand knowledge, it reshapes imagination. And we are only at the beginning. Future instruments promise even greater leaps. Projects like the Square Kilometre Array, under construction in Australia and South Africa, will dwarf today's telescopes in sensitivity and scale. It may detect FRBs by the tens of thousands, map their hosts across the universe, and perhaps even catch the faint afterglows that reveal their engines. With each new tool, the puzzle sharpens. For now, though, CHIME and FAST have given us the crucial insight. FRBs are not rare. They are everywhere. They flash and fade constantly, all across the universe, a hidden heartbeat of the cosmos. The mystery is not whether they exist, but what they mean. And thanks to our technology, we are finally learning to listen. When we reach the philosophical edge of the fast radio burst mystery, the science itself begins to blur into something deeper. Numbers and data points fade, and what rises to the surface is awe. Because whether FRBs are the tantrums of magnetars or the whispers of alien technology, their very existence forces us to confront our place in the cosmos. They remind us that the universe is not a silent void, but a theater of unimaginable power, filled with voices we are only just beginning to hear. If FRBs are natural, then they reveal phenomena of staggering violence and beauty. A single burst, lasting less than the blink of an eye, can unleash more energy than the sun produces in a year. Imagine that for a moment. Everything the sun gives us, the warmth on your skin, the light that feeds every plant, the power behind every storm, all of that sustained for 365 days, poured out in an instant from some invisible source billions of light years away. The fact that such power can be compressed into such brevity stretches our imagination to the breaking point. It reminds us that the universe operates on scales of energy and force that human intuition is almost incapable of grasping. To encounter FRBs is to be humbled by nature's sheer audacity. And yet, if FRBs are artificial, the implications are even more profound. To harness that much power and direct it across the universe would require a civilization far beyond our own, a culture that has mastered its environment to a degree we can hardly dream of. We would be glimpsing not just alien life, but alien genius minds that think on scales of stars, technologies that use energy as casually as we burn wood. Even if they are not meant for us, even if we are eavesdropping by accident, the message would be undeniable. We are not alone. The cosmos, vast and dark as it is, might be filled with intelligence, each one perhaps sending out its own radio thunder across the gulfs of space. But perhaps the deepest lesson of FRBs is not in what they are, but in how they make us feel. Whether natural or artificial, they remind us of our smallness. Here we are, on a pale blue dot, orbiting an average star in an average galaxy, listening to signals older than our species, older than civilization, older even than Earth's mountains. These bursts traveled billions of years to reach us, crossing cosmic distances so immense that whole galaxies have risen and fallen in the time it took their waves to sweep through the void. And yet, when they arrive, they are captured by fragile instruments built by hands like ours, decoded by minds that still struggle to understand themselves. That is a miracle of perspective. The philosopher might say that FRBs are a kind of cosmic mirror. When we hear them, we don't just hear the universe, we hear ourselves reflected back. Our curiosity, our hunger for meaning, our refusal to let the unknown remain unknown, all of it is wrapped up in the act of listening. The bursts themselves may not carry a message for us, but the fact that we listen, that we search, is its own message. It says something about what it means to be human, to look up at the night sky, to strain our ears against the silence, and to wonder. There's a humility in this. Every time science solves a mystery, the horizon only expands. We thought Earth was the center until we discovered the sun. We thought the sun was the center until we discovered the galaxy. We thought the galaxy was the whole until we discovered billions of others. Now, with FRBs, we glimpse processes that operate across billions of light years, hinting at forces and perhaps intelligences far beyond us. Each step strips away our illusions of importance, but it also enlarges us. The universe grows, and so does our awareness. And still, the mystery remains. Perhaps that is the point. Perhaps the universe is not meant to be fully grasped, but to be engaged with. FRBs are not just puzzles to be solved. They are reminders that reality is deeper and richer than we can imagine. They tell us that there are still frontiers left, even in an age of satellites and supercomputers. They whisper that the cosmos is alive with mystery, and that our journey is far from over. In this sense, FRBs belong as much to philosophy as to astrophysics. They ask questions that equations alone cannot answer. What does it mean for the universe to be filled with voices we cannot yet understand? What does it mean for us to be listening? Are we hearing nature's power or another intelligence's intent? And does it matter which? Perhaps the true message of FRBs is not about their origin, but about us, about a species that builds machines to catch whispers in the dark and dares to wonder what they mean. In the end, the message is clear, though not in words. It is a message written in power, in brevity, in the sheer fact of existence. The universe is alive with mystery. And in that mystery, we find our place not as masters of the cosmos, but as participants in its unfolding story. Perhaps the greatest gift of the fast radio burst mystery is not the promise of answers, but the experience of the questions themselves. Science, after all, is a story one that unfolds with every discovery, every experiment, every unexpected turn. In this story, FRBs are the latest chapter, and like all good chapters, they carry both suspense and revelation. For centuries, humanity has encountered phenomena that seemed impossible. Lightning once felt like the wrath of gods until we discovered electricity. The regular pulses of pulsars seemed too precise to be natural until we realized they were the spins of dying stars. Gamma-ray bursts were cosmic enigmas, unexplainable until we found their roots in supernovae and neutron star collisions. Each time, what seemed supernatural eventually found its place within natural law, expanding our understanding of what the universe is capable of. FRBs may be no different. Perhaps they are the tantrums of magnetars, the last breaths of collapsing stars, or the echoes of collisions in the deep. If so, they will join the long list of wonders that once baffled us, but now stand as monuments to the universe's creativity. And yet, there remains the other possibility that FRBs are not just nature's fireworks, but something more. That they are signs of intelligence, beacons sent across the dark, or the side effects of technology so advanced we mistake it for natural. This is a possibility so extraordinary that it demands skepticism, but not dismissal. For the history of science is also the history of daring to imagine. The very act of considering that we might not be alone, that we might be hearing the work of civilizations across the cosmic sea, forces us to stretch our sense of what is possible. It reminds us that our imagination must always be larger than our current knowledge. Whatever their origin, FRBs have already achieved something profound. They have captured us. They have inspired headlines, debates, and late-night conversations. They have pushed us to build new telescopes, design new algorithms, and listen harder than we ever have before. They have turned radio static into poetry, into a mystery that binds astronomers, philosophers, and dreamers alike. In that sense, their meaning is already clear. They are catalysts, sparks igniting the fire of curiosity in a species forever hungry to know. Think of what it means to be here, now, listening. We are listeners standing at the edge of a vast ocean. Each FERB is like a wave washing against the shore, carrying whispers from across billions of years. The bursts began their journey before our planet had trees, before humans walked upright, before our ancestors even dreamed of the stars. And yet they arrive now, in our time, when we have built the ears to hear them. It is as if the universe was always speaking, and only now have we grown quiet enough, clever enough to notice. Perhaps one day we will decode them. Perhaps we will learn that FRBs are the quakes of magnetars, the collisions of stars, or the hiss of cosmic strings snapping. Perhaps we will find messages buried in the noise, codes written in millisecond pulses, greetings from across the void. Or perhaps the truth will elude us still, and FRBs will remain what they are now, reminders that the universe is larger, stranger, and more alive than our minds can yet grasp. But even if the answers come, something of the mystery will remain, because the real lesson of FRBs is not about what they are, but about who we are. We are the species that listens. We are the ones who turn dishes of metal and wire toward the sky, waiting for whispers. We are the dreamers who dared to imagine that the universe might be speaking to us. That imagination is not trivial. It is the heartbeat of discovery. Without it, we would never have crossed oceans, split atoms, or walked on the moon. With it, we may one day walk among the stars themselves. So as we close this chapter, perhaps the most important reflection is this: the strange signals from deep space remind us that we are part of something vast. We are not at the center, not the masters, but participants in a grand cosmic symphony. Every FERB is a note in that symphony, sometimes chaotic, sometimes rhythmic, always mysterious. To stand on the shore of this cosmic ocean and listen is to take our place in the orchestra, to recognize that the music was playing long before us and will continue long after. The edge of understanding is not the end. It is the beginning. FRBs are not answers, but invitations. Invitations to build bigger telescopes, to think bolder thoughts, to push harder against the silence of the sky. They invite us to humility, reminding us that the cosmos is older, deeper, and stranger than we can yet comprehend. And they invite us to wonder, to let our imagination stretch as far as the bursts themselves have traveled. Perhaps one day, we will understand the language of the stars. Until then, the mystery is enough, because in listening and straining our ears to hear the faint whispers carried across time, we discover not only the universe, but ourselves.